So, good afternoon to you all, and on behalf of Jawaharlal Nehru Planetarium and ICTS, International Center for Theoretical Sciences, I extend a very warm welcome to you to this edition of Kaapi with Curiosity. So, we have the speaker, Professor Sarita Vig, and the topic is very, very interesting, finding our place among stars. So nice to be among stars. So we feel ourselves to be elevated to the status of a star in a very metaphoric sense. So we look forward to a very interesting presentation about on this topic. And just before I request Professor Rukmini Dey to introduce the speaker, I have a small announcement to make, which would be relevant to all of you who are present here. This is to inform you that Jawaharlal Nehru Planetarium has come up with a new program beginning this year. It's called Dasara Lecture Series, which is inspired by the Christmas Lecture Series by the Royal Institution. We have a long way to reach there, but then we make a modest beginning this year. And the idea is to have a set of 4 or 5 lectures on interdisciplinary aspects on a particular theme. So the theme of this year's Dasara Lecture Series is structures at different length scales. So right from atomic and molecular level, all the way up to cosmic structures. So there would be 4 different speakers who will unravel the structures in the field of their specialization. So we have a galaxy of scientists, Professor Tarun Shauradeep, who will be speaking on cosmological structures. And then we have Professor Rama Govindrajan from ICTS, who works in the field of clouds, monsoon, and weather prediction. So she'll be talking about structures that she comes across in her field of specialization. And the third is animal-built structures by Tejas G. Murthy from Civil Engineering Department. So you might be wondering what animals and civil engineer have in common. So quite a lot, if you see. So that's the interdisciplinary aspect that I just mentioned to you a bit earlier. And the final lecture will be on October 1st, which will be by Professor Uday Maitra. He is from the Department of Organic Chemistry, Indian Institute of Science. So his talk is titled as Chemistry is Fun, but then he will be talking about all the structural changes that take place at the molecular level that bring out all the wonderful chemical reactions that we see. And his lecture will be profusely demonstrated with some exhilarating experiments. So color changes, flashes of light, sound and whatnot. So please do come. This is from 28th of September to October 1st. It will be held at the same time, 4 o'clock on these 4 days. It's open to students, basically aimed at high school students and early college students to inspire them to take a career in science. And general public who are very keenly interested in science like you all are welcome. So please do come and make it a big success. So that's the announcement I wanted to make. And I now request Professor Rukmini Dey to introduce the speaker.
Thanks, Professor Madhusudan. So hearty welcome to everyone. I'll say a few words about ICTS. It is a center of TIFR, which is dedicated to research, programs, and outreach. And Kaapi with Curiosity is one of our numerous outreach activities. And it is held jointly with Jawaharlal Nehru Planetarium. So today it's my great pleasure to introduce Professor Sarita Vig. She is a professor at the Indian Institute of Space Science and Technology, IIST, Thiruvananthapuram. She has completed her PhD from TIFR Mumbai in 2005, which was followed by a postdoctoral position at the Arcetri Observatory, Florence, Italy, till 2008. She was the PI of a project at IIT Madras till 2010, when she joined IIST. Her research interests include early phases in massive star formation, galactic clusters, interstellar medium, and galactic structure. She teaches astrophysics to students pursuing their bachelor's and master's in IIST. She is also interested in astronomy outreach activities and loves to talk to people about the cosmos. So today we'll hear her talk about finding our place among stars. So before we start, I would request Professor Madhusudan to hand over a memento to her. Over to you, Sarita.
So good evening. Am I audible? Yes? Okay. So it is my pleasure to be here and talk to all of you. And thank you very much to ICTS and JNP for this invitation. I'm always happy to talk to people and answer their questions. And I hope there will be questions at the end. I will be happy to answer them as much as time permits. So today I will be talking about finding our place among stars. So let us first start off with, where are we? So where exactly are we? Only when we know where we are here, we start off from what we know, and then we try to see where we are among stars. So our place on Earth, I'm sure you know where you are located on Earth. Yes? Where in Earth? Bangalore, right? But you are all like, have visited a number of places, and you know precisely the latitude and longitude of those places, isn't it? We know the location on Earth because we have defined certain coordinates, and we are able to pinpoint. So the moment you say Bangalore, people are able to say exactly where you are on Earth, right? Now let's go a bit farther out, okay? So I'll be going farther out, and towards the end I don't have answers, but we'll go about as far as we can. So what about if you go outside Earth? What is our place in the solar system? Well, do you know that? Yes, we all know that, isn't it? Our solar system comprises of our sun. Sun is a star, very important for us, of course, because of all the life that is growing here is because of the presence of sun. But that is not all. In the solar system, we have a number of planets, right? How many planets are there? 8 planets. When I was young, your age, his age, there were 9. Then somewhere along the way, one planet was demoted and became a dwarf planet. So it's not something that everybody can answer very instinctively. Okay, so that's the reason. Many of you are very young, you may not understand this aspect, but for me it's very important that somewhere along the way we decided to define planets better, and in the process Pluto was demoted from a planet to a dwarf planet. But among these planets, where is Earth located? Also we are very clear, right? You have, next to the closest planet to the sun is Mercury, then you have Venus, then you have our very special Earth, then you have Mars, and then you have asteroid belt, Jupiter, right? Saturn, Uranus, Neptune, and then you had Kuiper belt. I mean, I don't know if you have heard of these kind of objects. The point is, as you have seen here, most of them are lined up here. You know, right? They are all lined up. And when many of you have drawn solar system in school, right? And how did you draw the solar system? You not, even we. How did we draw the solar system in school? It was in geography. You drew the sun, and then you drew very nice circles around them, right? To show, which is what is shown here, correct? I just want to draw your attention to one small bit, right? Why are all these planets lying in the same plane? In principle, have you thought about it? Why are all the planets, when we draw, it's easier, no, to draw like this. We always draw like this. We never, but in principle, every planet can have an orbit of its own, right? But it is not like that. Question is it only for drawing, or is it really like that? Okay, that's the first question you should be asking. And the answer is, it really is like that. It so happens that all these planets seem to move roughly in a plane, which brings us to a very interesting question, why? Okay, and I'll come to that bit, and that is why I want to just tell you about quite accurately. Okay, but what about suppose we go outside? So how do we define our solar system? Our solar system is comprises of many planets around a sun. So sun is a star, right? All of you know this. And what is a star? Something that is held by self-gravity, definition of a star. Something that is held by self-gravity of its own and which is producing energy mostly by nuclear fusion reaction. Okay, you can't say just nuclear fusion reaction because that even in a nuclear reactor you are doing. Okay, so it has to be by self-gravity. So that is how you roughly define what a star is. Now, where does the sun lie with respect to other stars? That's our next question, right? And that's what in this talk I will be trying to reach towards. So this is a question that intrigued many astronomers from a long time, right? In the universe, where are we? So when they started looking around, all of you I'm sure have seen the night sky, have seen the stars, right? I don't know in Bangalore if you can see the Milky Way. I am not sure. Is it possible? No. But you have to go outskirts of Bangalore to see. Any of you seen Milky Way in our naked eye? Raise your hands. Yeah, some of you have, right? So let us now imagine those very old astronomers when there were hardly any lights. It was blissful time for them. They could actually look up and see the Milky Way and realize that everything is not uniform in all directions. So along some directions, some things are different, right? And it was first Galileo who came to the kind of conclusion that what you see as a faint band of light, if you have seen the Milky Way, you will not be able to distinguish individual stars. You will just see it as a faint band extending. And he was the one who came up with the idea that these are actually a number of stars, more density of stars in that direction, and therefore the density of stars is not uniform in all directions. And that's how, and probably we are part of this system. And that is when people started thinking that the distribution of stars is not uniform, but this is how our universe is. There's more stars in one direction, in some specific directions as compared to the other directions. And then there were more ambitious astronomers, right? There were people who came up with theories. Like there were at that time, physics, chemistry, astronomy, philosophy, it was all together. You couldn't find people who say, I do only astronomy or I do only chemistry. So there were these philosophers, Immanuel Kant and others, who came up with the idea that this is like one particular universe, and then you may have other universes. What they called as a universe is what we call as a galaxy now. I'm just telling that to you in the beginning. But this was their idea, that you may have other such systems outside. Then some people said, okay, if that is the case, first let us try to understand this system itself. And do you know what they did? They started counting stars. Now, usually we will not begin counting stars, will we? We count sheep when we go to sleep. Yeah, if you are in the open, you will count stars and probably go to sleep. But there were people who actually stayed awake to count stars because they wanted to know the distribution of stars. And Herschel was one such person. But when you do such a thing, we are always intimidated by this problem, right? If I say count the number of stars, isn't it? Will we be intimidated, or we'll say, yes, let's start? But the point is, whenever you have a big problem, you have to break it down into small and make some simplistic assumptions. Then life becomes simple. Then you can start coming back and make it more complicated. Usually we are always thinking about the complications first. So Herschel, for example, what he did was he's made some simplistic assumptions and said, okay, let me assume all the stars are of same brightness, density is more or less similar in some of the regions which I'm going to see. And he tried to make a model of this universe, as it was called at that time. And that is the picture that you can see here. This is the first recorded 2D map of what is we now know as our galaxy. Okay, and in the 18th century, right, by counting stars in different regions of the sky and trying to understand. And then there were other astronomers. This was, of course, there was a lot of, efforts in this direction. And I'm directly jumping to 19th century after this, because during the intermediate stages, people were still trying to figure out, make larger telescopes, trying to understand the various objects and so on. And then people are still trying to understand the structure. In this model, roughly the sun was at the center. But later, then there were other people, I won't go into details, who used different kinds of objects. Example, something called globular clusters, a group of stars, which are a very large group of stars, spherical in shape and so on, that is distributed everywhere across our galaxy. So there was this person, Shapley, who actually started studying these specific clusters, and he found that they're distributed everywhere. He used that distribution to make a map of our galaxy, and he got something which was very different from what this is. He found that, of course, there were pitfalls, because again he made some simplistic assumptions. He assumed that you are seeing stars and nothing is there between stars, which is not really true. There is, in the medium between stars, it's not fully vacuum. There can be very small, less amount of dust particles and gas which is present that can reduce the starlight reaching us. But because they did not consider that this could be there, they got distances to very large scales. And he also made a map, but according to that map, the size was much larger than what Herschel's map was, and the sun was not at the center, but it was away from the center. I will not go into all those historical details. But at the same time, so this is what was happening in our galaxy, where people were trying to understand where we are located with respect to other stars. At the same time, there was a lot of development happening in trying to understand some specific kind of objects. You are all familiar with Messier objects, right? Messier catalog. This Messier catalog was started when, he started recording these objects because he wanted to discover comets. So he started recording whichever fuzzy objects are there in all directions, and that's how the Messier catalog came about. They are fuzzy objects, and he thought that he didn't want to confuse these with comets. At the same time, there were other people, New General Catalog was made by another set of people who were trying to locate these nebulae, as we are called. They are not stars, they are more extended fuzzy nebulous objects. But when they were looking at some of these nebulous objects, they found some of them to have, in fact, in 1845, when the largest telescope at that time was built in Ireland by Parsons, and he found that when he looked at some of these nebulae, that they had spiral shape, like pinwheel. Pinwheel, firfiri. You know what's firfiri? You roll up paper and you put a pin. Okay, so these pinwheel kind of structures were seen in some nebulae, which was spiral nebulae. And that's where once you see spiral structure, what's the thing that comes to mind? Some rotation effect is happening there. Okay, that there is some rotation which is happening, but you don't know because you are in the 1850s, right? Is it really rotating or not? And then in the 1912, Slipher, one person, he was working with the spectrograph, and using radial motions, Doppler effects, he found that these are actually objects which are moving farther away at very large velocities. Okay, and they were kind of, that rotation effect couldn't be seen, but he found this. So this kind of gave rise to a kind of problem, because it kind of distributed the astronomers into two groups, the spiral nebulae. Immanuel Kant, this philosopher, he gave the name the spiral nebulae as island universes, because he thought they are universes like ours. Basically, they are other galaxies, because our universe was our galaxy, right? That they are something outside our galaxy, not the same. But then there was a set of people who, based on the observations which were present, felt that they are far off objects, but they lie within our galaxy. So there was this huge confusion. What about these objects? And that is what gave, so there was a lot of confusion. People were trying to understand this, and to sort out this confusion, you know what they did? They came up with the idea of, okay, have two groups which are represented by two people, we'll have a debate. And that is the famous great debate about the island universes. Okay, so are they within our galaxy or are they outside the galaxy? So this debate was between Harlow Shapley, who actually represented the idea that they are objects within our galaxy, and he had already made one model of the Milky Way, so he was continuously talking about that, and say his model, according to his model, galaxy was very big, and 300,000 light years, I mean very huge, and these are objects within that, and he used some observations which were later turned out to be flawed observations to emphasize the fact that they belong to our galaxy. And the other person, which is Herbert Curtis, this happened in 1920, he actually said that these are large and distant objects which are rotating just like our galaxy. These are also flattened structures, but they are outside our galaxies. So they are other structures like ours. The point is, at that time, if you look at the observations, what did the great debate achieve? The great debate did not help in solving the problem in the debate. What it did help to do was to list out problems and list out the current observations very clearly for people to work on. So it did not have an answer in terms of a winner. But of course, Curtis was declared winner because he could speak very well. But that's a different point. The problem essentially boiled down to problem of distances. So as long as you don't know to what distance this object is, you cannot tell whether it is an our galaxy or outside or it's a separate galaxy. Also, you need to know the distance of our galaxy. How big is our galaxy, right? But this problem was completely solved in 1923-24 by Edwin Hubble, who measured the distance to this and nebula, spiral nebula in Andromeda constellation now known as Andromeda Galaxy, and he found the distance to be very large, around 1 million light years. This is not a correct distance. The correct distance as we know today is 2.5 million light years, but of course if you consider the errors, the simplistic assumptions they made, but this definitely put down the fact that this kind of spiral nebulae did not belong to our galaxy. They are something else. Now I've been talking about, if you are interested in this debate, the transcripts of this debate can be found here. But the point is, I've been talking about galaxy and so on for a long time. I've gone very far off, is it? Yes. So now we see a lot of galaxies everywhere. Okay. This picture is of a picture taken by Hubble Space Telescope, NASA's Hubble Space Telescope, which has been imaged very deeply. How deeply? I mean, you continuously take the image so that you can see very faint objects. This picture, for example, has 10,000 galaxies. It's a very small portion of the sky, around 11 arc-minute square, but it has 10,000 galaxies. Now we see these kind of galaxies everywhere, okay? And we also know the distances to a large extent. But at that time, this was still being understood. Okay, so what exactly are galaxies? Let me first introduce the concept of galaxy, right? As we understand it today. So I'll keep moving a bit back and forth. So what is galaxy? Galaxy is a large aggregate of stars, a very huge group of stars, okay? Not only stars, it can also have the interstellar medium, which I talked about, some gas and some very small amount of dust particles between stars. When you look up at the night sky, between stars, you don't see anything. But nebulae, when you see nebulae, you see diffuse objects, right? That is the gas and dust, that's interstellar medium. So it is made up of billions of stars, gas and dust, all held together by gravity, and these are scattered throughout the universe. And of course, not all of them are alike. I'm sure you know this. They are categorized into spiral galaxy, elliptical galaxy, and irregular galaxy. Okay, and galaxies by themselves are not homogeneously distributed again. The galaxies are also grouped into clusters called galaxy clusters, and galaxy clusters by themselves are again grouped into superclusters. Is that right? So you have galaxy clusters and you have galaxy superclusters. So I'll just talk a little bit about how we identify these galaxies. Galaxies come in, these are only the specific broad types I'm talking about. When astronomers start working, you can find many shapes, and we actually categorize them like a biologist categorizes or classifies animals in a zoo. We need to categorize galaxies in a specific class. There are so many of them of different kind. You can't fit them all into these. But broadly, yes, it's like saying plants, animals, and mushroom. Okay, so you have elliptical, spiral, and irregular. Okay, so what are elliptical? I've shown an example below. They are like, you know, egg-shaped structure, more symmetrical, of course, where the density of stars, what you're seeing is the diffuse light, they're actually stars. Okay, it's all, if you are able to resolve them, you will see them as stars, high density of stars, which is giving this kind of feel which you are looking at. And then you have spiral galaxies. where you have the stars distributed into spiral shape, flattened structures, and so on. And then you have something which doesn't fit into either of these boxes. They are known as irregular galaxies. Now, if you look at these elliptical galaxies, spiral galaxies, I have shown some color, I've used some color coding. So the blue stars, for example, in blue stars represent the heavy mass stars, but that is not true for all the elliptical galaxies. So you can have in the spiral galaxies, you will see a lot of these structures. These are due to blue stars. Blue stars are heavier stars formed recently, and they are mostly formed in the spiral structures. Remember, you are able to see the spiral structures because of the presence of stars in the spiral structures, right? So that means stars form preferentially in the spiral structures. So this is something that you must bear in mind when you're looking at spiral galaxies. And then you have this irregular galaxy where you can have a mixture of the two. So now, what type is our galaxy? What type? Everybody knows the answer to this, right? Spiral galaxy. How do you know? You are sitting inside the house, right? You are sitting in your house and I am asking you that what is your house type, correct? You have come across this kind of pictures which shows you and gives you a very clear picture of what our galaxy looks like. Don't take stuff seriously. Remember, you are here. How is it related to galaxy? But you got the idea, right? What is the idea? It tells us that we are very insignificant. We humans are very insignificant. Our problems are even more insignificant, small temporal. I completely subscribe to that philosophy. I like it also. But what I don't like is the picture. Can I get a picture of my galaxy like this? To get a picture of my galaxy, I will need to go outside my galaxy. But nowhere it is written representation, artistic representation, or picture which is only used for representational purpose. So I have a problem with that, because people think that that is the picture of our galaxy, right? Now I'll show you something else. And they also tell you that you are here in that galaxy. They are actually pictures of some other galaxies. So if you see this picture, you are in 4 different galaxies, right? They are all spiral, nice, well and good, all real pictures, well and good, and all of them say, you are here. They will never say, I am here, okay? They'll always say, you are here. So it's your problem, correct? Next time, this is a suggestion. Next time you see a picture, you say, fine, you may be there, I am not there. Because my galaxy picture cannot be like this, cannot be taken like this, isn't it? So this is something I want to convey, how difficult it is to take a picture of our galaxy and how we go about doing this. That's what I want to talk about a little bit. Okay, so that brings us to the question that where is Sun in the Milky Way, right? Where is Sun in the Milky Way? But coming to spiral galaxies, do you know how it looks like? It's flattened, we said, right? It's flattened and has spiral structures. I'll come back to what a spiral galaxy looks like in more detail as we move along. So if you have looked up at the night sky, this is a wonderful picture which actually shows in detail the stars, and this is how the Milky Way looks to us. We are sitting in the Milky Way, yet we want to know that it is a spiral galaxy because you all know it's a spiral galaxy, right? But how do you know? You know because somebody told you, isn't it? It's not something that comes automatically, right? So let us look at trying to understand this. So as I said, it is like mapping your house, okay? Not just mapping your house, you are tied to a chair, right? And I am asking you, please give me the architecture of the house while you are tied to your chair. You can do any experiment you like, okay? You are allowed to do any experiment you like, but you must tell me how your house looks like, okay? So you can think of whatever ideas. I will use laser beams, I will use beams which can penetrate the walls, etc., etc. You do whatever experiment. but that's what we are forced to do in some sense, metaphorically, right? But at the same time, you need a perspective which is complete in every sense. How does it look from outside? Okay, because once you are within the house, there will be limitations depending on what technique you use, always, okay? And of course, if you are looking only in one direction, it will be like this story. You all know this story, no? You will be looking only locally, and then you will say, this is like a fan. Our galaxy is like a fan. Our galaxy is like a rope. We don't want that. We want the full picture, okay? So the answer to this question is to measure distances to stars, right? And measure distances to as many stars as possible. You want to make a 3D map of the galaxy, right? That's what you were doing with your laser, right? Measuring distances to walls and then further walls and so on, in some sense. So you need to measure distances to stars and a large number of stars to be able to make this picture of the galaxy. So how do you do that? Okay, one simple way I will tell you, okay, and that is known as the parallax method, which is used to measure distances to stars. Now when you are traveling in a train or in a bus, what do you observe? You observe the trees are moving, trees, mountains, outside whatever is there is moving in the opposite direction. Yes. Now if it's a tree or if it's a tree versus a mountain, mountain is very far off, tree is very near, and you are traveling. Which one will move faster in the opposite direction? Tree. Have you thought about this? Yes, always you observe this. This is what is used to measure distances. You see the fact that how fast it is moving against you to measure the distance to that. Essentially, it's this. So here the earth is moving, right? Earth is moving around the sun. So as the earth is moving, the star appears to move in the opposite direction. And when it is coming back, the star appears to move here, right? So it seems to move in different positions. And we use this fact. So if you know how much it has moved, and you know, basically when you know how much it has moved, you have measured this angle. How much it has moved from here, when the tree is moving from here to there, that angle if you are able to measure, and you know how much distance you have traveled, that means you know this distance, then you can calculate this. Okay, it is as simple as simple trigonometry, tan theta. So this is your theta, and you know this one astronomical unit, that is the distance between the sun and earth. From that you can calculate the distance to the star. So this parallax method is the simplest way to measure stars to the nearest distances. Did everybody get this point? Parallax method, it's the same concept which helps you to intuitively answer that question, that why close by objects move faster when you're traveling in a train as compared to the farther objects. It's the same concept. Okay. So what would happen if you are doing many circles around the sun? Can you imagine what this star will be doing in the sky? Are you getting my question? The star seems to move, right? Now, you translate it to the train problem, because the train problem is easier for us to imagine. I'm moving in circles. What happens? The tree keeps going back and forth, back and forth, back and forth, right? Mountain keeps also going less back and forth, but it does, right? Same way, depending on how much big circle you are making. In the same way, when we are looking at parallax, as we are moving, completing one circle, the star also appears to make a small circle in the sky in the opposite direction. Using how much that angle radius it is making, we can basically, based on the motion that it is making in the sky, that circle, don't worry about the details of angle and all, we can calculate the distance to the star. And the farther the star is, the smaller the circle it will make. The closer the star is, the bigger the circle it will make in the sky. So you can measure the distance to the star. Okay, that is the same example which I was talking about. But other than that, stars have also other motions. Okay, I want to bring this up. So is this the only motion of stars? No. The stars, the whole galaxy, particularly if it's a spiral galaxy, Even elliptical galaxies, the stars are moving slowly about the center. And in often when you see flattened structures, it means that they are rotating structures, because of rotation only you can get flattened structures, otherwise they will be spherical. So when you say spiral, that means the galaxy, the stars in the galaxy are moving. So which means apart from parallax motion, there is some inherent motion of the stars. Yes, some inherent motion because of where you are located away from the center, that motion will be there about the galactic center. Plus, suppose one star comes, another star is going by, this star is going by, they will kick each other and go. That motion is also there. Explosive, suppose some explosion happened there, it got some kick. So stars can have some inherent motion. So this is inherent motion is the true motion of the star, and the parallax motion is the apparent motion. Okay, apparent means they are not moving. It gives the appearance. Is the tree moving? No, it's an apparent motion. So you must be able to distinguish between the two. So this is the inherent motion of stars. Now how can you measure the motion of stars? Do we have a paper? Okay, I don't have a paper, I have a folder. Okay, I want to explain to you. When you look at the sky, what do you see? You see it something like a dome, is it not? If you're standing here and looking, you are in a desert. How does the sky appear to you? It appears like a big dome, huge dome, is it not? Now I concentrate on a very small part of this dome. How does the sky appear to you? Flat. Yes or no? Suppose a star is moving, will you be able to see? No. That is because, suppose it's moving very fast, will you be able to see? Very fast, so that you can see. Will you be able to see? Always? No. Yes. Which is it? Okay. So let me tell you. Okay, I'll use this. Assume this as a, for a moment, assume this is a point-like object star. Okay. Now this is moving in some direction, but you can see only this plane. You can see this is your sky plane, that small part of the star, but the star is moving like this. So this velocity I can divide into two components, one in the plane of the sky, one along my line of sight. This is radial motion. I will not be able to see if the star is moving radially. Will you be able to see? It's moving like this, like this. You will be, by seeing you won't be able to do. By Doppler motion you will be able to find out. If you don't know Doppler motion, it's okay, but you can think about it. Using some technique we can find out. But by looking, you won't be able to make out. You will be able to make out only if there is motion in the plane of the sky. So you are breaking up the velocity component into 1 and 2 dimensional components. 2 dimensional component is in the plane of the sky. That's called the tangential component or the proper motion. So that we will be able to see when we are looking in the sky. You are getting the point? That is the proper motion. Radial motion you will be able to find out only by using other techniques. Just by looking I won't be able to see something going. Suppose somebody is going away or coming towards you, you are able to make out that motion only because of the size change. Remember this. You are not able to make out because of any other reason. But if it's a point-like object, you won't be able to make out, right? Anyway, so basically that's what I want to tell you in this slide. So you have the radial velocity and you have the transverse velocity, which is known as the proper motion. Okay, so if you are measuring either radial or proper motion, you are not getting the full velocity information. You will get full velocity information only if you have both of them. Okay, so we use, in fact, all these motions of the star, the distance to the star, to be able to get a full knowledge about how the stars are moving and how the stars are distributed in the galaxy. But it's a very difficult question because the galaxy is huge. We can't do it to a very far stars. You can only apply these methods to close by stars, because the farther you go, that angle will become chota, 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 and then you won't be able to make out at all. Okay, I mean the angle will become small, 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 and you won't be able to make out. Okay. So there was this mission called Hipparchus, which was a space mission sent by astronomers who were interested in kind of trying to solve this problem. They wanted to measure the distances to as large number of stars as possible. That was in the 90s. Okay, and they got the distances to a large number of stars. Okay, but there is a new mission now which wants to expand this even further. You want to be able to go as far as possible. That is known as the GAIA mission. It was launched by the European Space Agency in 2013, started taking observations in 2014. You know, its aim is to build the 3D structure of the stars, of the galaxy, using stars by measuring distances to stars. How? By parallax method. Because it can measure even small amount of that motion. And it also measures radial, it also has an instrument to measure radial velocity. And since parallax motion, it has to measure the movement of stars, it has to consider the effect of inherent motion also. You can't leave it out. That will be much smaller, but it will be there. But they are able to measure that also. So its main ambition is to chart a 3D structure, make the architecture of our galaxy. Okay, what is the architecture? Find out. So this picture, this is a video, okay, which shows the motion of the stars, proper motions and parallax. First, you will observe these motions are measured by GAIA. Okay, can we switch off some of these lights, please? Because I am not sure it's visible. Yeah. Can you see the motion of stars? What is that motion? So what motion is that? No, it's parallax, because it keeps moving this way continuously. It's the parallax, isn't it? So now you are seeing how the stars in the constellation, how their motion is. So what do you make from this? Okay, I'll come back to this again. Let me go back one slide. Okay, so I'll just explain. No, please don't switch on yet. I have a couple of videos. First, I just want you to focus on the fact that in the video that will come up, there is a picture 360 degrees view of the sky which is opened up, and you will see stars initially showing parallax motion and then later proper motions. They are enhanced or amplified so that you can see. Obviously, we can't see with our eye, but they are amplified by 10,000 times parallax and a trillion times for proper motion. After that, what you see is before proper motion comes in after parallax motion, you will see the constellations coming up and different stars, how they are moving in parallax motion, you will be able to see. And you will find that different stars in the constellation make different circles. What does that tell us? That the stars in the constellation are at different distances from us. It's only their projection we see as a constellation. But in reality, all these stars in the constellation are at different distances. Then what will come up is the proper motion, the inherent, after you remove the parallax motion. Suppose from the star I remove the parallax motion, then some motion will be left over. What is that motion? That is the proper motion. You can see again different stars have, that is amplified many times, but it gives you a picture of how the stars are actually moving. Some stars are moving by small amount, some by very large amount. Okay, shall we start? Okay, now you can see the motion will start. Can you see the parallax motion? Right? And some are fast, even here some are moving big circles, some small circles. Big circles means closer. Small circles means far apart. Very small, almost not moving means very far. Okay, now you see the constellation. They are moving by making different circles, right? So what does that tell us? Stars in the constellation are at different distances from us. Okay? Now comes the proper motion. You can see how the stars are moving in the constellation. That's very small amount. You can't see the change when you see with the naked eye because it's amplified by 10 power 12 times. But now you can see the constellation lines are removed, how the different stars are moving. Can you see that? That's the actual inherent motion of the stars. After you remove the parallax effect, these are how they are moving. They have certain velocities. But these are these proper motions or are these radial motions? What are these? Proper motions, radial motion you cannot see. This is only the motion in the plane of the sky, right? Okay. So GAIA is doing a very good job in this way. Please don't switch on light. I have one more video. Next video will show you how GAIA actually has already collected quite some bit of information, and nearly 2 billion stars they have. Look, our galaxy has about 200 billion stars. Of that, 1% is what their aim is. 2 billion stars, they want to measure the parallax proper motions as much as possible. So the next video actually shows you how they have built up the structure of the Milky Way close to the sun for the nearby stars, because the farther you go it becomes more difficult. So they had 2 sets of data release. Once they released first and second. When they released the second data release, they were able to go farther because they got more accurate information about the stars. So both are from GAIA, but the second left is first data release and right is second data release. So this is the sun. Now they have made this 3D structure and then they are moving out to show you how the structure of the galaxy is. So we are moving away from the sun. We are going out, okay? And this is how the actual distribution of stars is in the Milky Way based on GAIA. Remember, this is actual information. You see how big our galaxy is and how much have we covered? Just a very small portion of it. Yeah, you can switch on the lights. So GAIA is, I'll take questions later. Okay, so GAIA is trying to do that, all right, through this method, through the parallax method. But this is not the only way by which you can measure distances to stars, because if this was the only way by which you could measure distances to stars, then you would not know about the entire galaxy. Am I right? You need some other methods. And we have other methods. They are more involved methods, complex methods. I won't be going into too much detail. All I will tell you is we use the effect of rotation of the stars or objects around the galactic center to be able to tell its distance. We use models, okay, based on rotation effect to be able to tell how far it is from the center. So we usually, in this case, we don't use stars because you can't see stars which are very far off. We rather use nebulae, ionized nebulae, and we use the kinematics. We use their rotation. We find out how they are moving with respect to us. We use the radial motion, proper motion, whatever is possible, very often radial motion, and we use certain models to be able to tell us, okay? And we use the relative radial velocity. You can measure this radial velocity using Doppler effect for spectral lines. I will not go into more details than that, and using some models you can measure. This is a nebulae, for example, just to give you an idea of what a nebulae looks like. And this is actually from one of the papers recently, just to give you an idea of how they have used these nebulae, young nebulae called H2 regions, to map the structure. And you can see more or less it seems to have, you can't see clear spiral structures. This is a fact, you can't see, but you can see something which resembles a spiral structure. So next time maybe when we think of spiral structure of our galaxy, we'll remember all these things. There's so many uncertainties. We still don't know it fully. But this tells us that there are different arms, and actually these arms in our spiral arms in our galaxies are given various names. Perseus arm, Norma arm, Scutum Centaurus arm, Sagittarius arm, depending on which constellation that arm passes through. Okay, so there are different names given to these spiral arms also in our galaxy. Now I'll tell you the structure of galaxy as we know it. This is just 2 things I talked about, but in reality, a lot of astronomers are working on this using various tools which I was not able to go into to tell you that our galaxy roughly looks like this. You have seen how the galaxy looks like from top in the previous slide, that it has a number of spiral arms, but it is also very flattened. It has a disk, so from side it will look like this, and from top it will look like this. So you know this Diwali cracker, right? Which cracker I'm talking about? Yeah, chakra, charkhi, whatever. So when you look at it, does it look like a spiral galaxy? Does it have the spiral arms? When you are looking at the charkha, he can see spiral arms. If I buy it from shop, no. When you buy it from shop, it doesn't look like that, right? That time when you buy it from shop, you should see only from side. Then it looks like our galaxy. It has a disk and it has a bulge, which is what our galaxy has. But when you light it, is what you should see from top. That is when you have the spiral arms. Okay, so remember this picture of our galaxy. Our galaxy just doesn't have a disk. Towards the center, you also have some kind of spherical structure known as bulge. Okay, and now where is Earth, Sun located in this big galaxy structure? It is located quite far away. The size of the galaxy is about 100,000 light years, and we are located, the size is what we predict. We are located about 27,000 light years away from the center in the galactic midplane. We are not above. It doesn't mean that there are no stars here, but the density of stars here is less. Okay, it doesn't mean zero. It falls off. It is very less. And where is Sun located? Sun is located in the galactic midplane, about 27,000 light years away from the center. And towards the center, you have this distribution of stars in the form of a bulge, which is a spherical distribution. This is the architecture of our galaxy. This is architecture of most spiral galaxies also. But and we are able to draw a lot about this because we have seen other galaxies. Okay, otherwise, as you know, it's much more difficult to come to this picture. So we use other indirect means to try to find out as much as possible. And if I am here, now imagine you are in this density distribution of stars and you are located here. How does the Milky Way look to you? The Milky Way will look like a disk to you, because only along the disk the density of stars is high. Above and below, the density of stars is very low. That is why it appears like a band, because we are located in the disk. If we were located above the disk, we would get a nice picture of our galaxy, correct? We are not able to get that, right? So that's what I want to take. I want you to take away from this slide. And this is actually the picture of the various constituents of our galaxy. Let me just try to explain. This is the kind of top view. This is the center. At the center is a central bulge, what you see here. This is a cartoon which shows this. And the disk is also, as astronomers try to study how thick the disk is. Is there only one disk? Are there more disks? People do this, and they find that most of the stars are forming here. Even now they are forming in this, where there is interstellar medium, because stars from gas and dust. And that is mostly concentrated in a thin disk at this inner galactic plane. Then there is a thick disk of stars, which is older stars. Then you have bulge at the center. Then you have stars and clusters in the halo. This is called the halo. This halo also has some other material, which I will come to now. Apart from this, it is not plain. There is a warp. Can you see the warp? Warp means, where is that folder? I kept it in. Warp means, imagine this to be a circle. One side is going up, other side is going down. The reason for the warp, we don't know yet. There are a lot of speculations. We can talk about them later, but this is what people have tried to get even with GAIA observations. For example, this is with warp of the Milky Way. These green dots you see tell you the distribution of stars in the warp, showing the warp-like structure. Now there's something very interesting I want to talk to you about, the rotation of stars. Okay. Now the rotation of stars I showed you, right? What do you see? You see that stars are rotating about the Milky Way. As we know, the stars, the gravity as we know it, the gravitational law. What is the gravitational law? We all know Newton's gravitational law. If you consider the Newton's gravitational law, the rate at which an object is moving about another object depends on the mass, right? The time period at which, Kepler's laws, all of you are familiar, right? It depends on the mass, right? Now, if you have more mass in here, it will, if there is a certain mass, it will move with a certain velocity. Let us take the example of the solar system. You have sun, most of the mass is in the sun. So the sun mass is constant, right? The planet mass, is it that much compared to sun? Very less. But do you know the rate at which planets are moving around the sun? Do you know? You know, right? What about Jupiter? Is it moving, does it take same amount of time to complete one circle or less? Less or more? More. Do you know this? How much time just Jupiter? You may not know numbers. I'm not asking you numbers, but I'm asking you order of magnitude, right? If you go from Earth to Mars, to Jupiter, to Saturn, take some 70, 80, 90 years, right, to complete one revolution. Okay, that means they are moving more slowly. Yes or no? But in this case, the mass is constant. Okay, so if the mass is constant, they will keep moving more and more slowly about it. In the galaxy, what happens? There is mass is not constant, is distributed. But if you look at the distribution of stars as you go outside, it becomes less and less and less. So which means essentially mass at the center according to those stars is more or less constant. So you should expect the rotation at the edges should be slower, slower, slower. Yes, because Kepler's laws define your Newton's law of gravitation. Therefore, you will expect that the edges of the galaxy, as you are going away from the center of galaxy, the motion of the star should slow down. It should go down like this. But what people have observed from a lot of other galaxies is that it doesn't slow down, which is very, very strange. Okay? This is what you expect from the gravity that we understand, the laws of gravity that we understand. But it is not happening. Here you see this is moving fast, this is moving slow. But in reality, it is more like this. Beyond a point, it is constant. The rotation velocity is constant. And this is seen in very, very large number of spiral galaxies. So what does it tell us? There's something we don't understand. And that is where the concept of dark matter was introduced. Because if you see this, when we are saying how much mass is in there, what are we looking at? We are looking at light. The light coming from stars. So that's the luminous matter. But if there is some matter which gives off no light, but it is there, then it will have gravitational effect, right? And that gravitational effect gives rise to this flat rotation curve. So this flat rotation curve tells us that there is more matter. This is one interpretation, that there is more matter that is present than what we are seeing, and people label that as dark matter. Okay, now this is seen in very, very large number of galaxies, and most importantly, it is seen in our galaxy. But it's much more difficult to do these observations in our galaxy because we are sitting within it, but it is there. So this shows you actual data. Just take it as data point. These what points you see here and these lines as the telling us that the rotation curve is flat. As you go outside in our galaxy, the rotation is still happening at the same rate. All the density of stars is falling off. So people then model this and they model the rotation curve of the galaxy as various components. So if there was a bulge, then the bulge component will have this kind of rotation curve. Then you will have a disk will have this kind of rotation curve, plus dark matter will have this kind of rotation curve. And when you add up all this, it should more or less give you this structure. So dark matter is present in the halo. That's the distribution of dark matter which is thought of, and it is, and how is the density distribution? We do not know. Only there are various models people have proposed to understand this density distribution so that you can model the dark matter. Okay, so this is about the dark matter. Now coming to the last, I am on time, coming to the last important aspect, which is the center of our galaxy. What is in the center of our galaxy? Black hole. How do we know? Now we know because we imaged it. But before, because we have seen in other galaxies, you are able to see a lot of very energetic events that are happening near the center. That is why the presence of black hole was postulated. And then later with various observations, this kind of energetic and violent phenomena at the centers of galaxy can only be explained by the presence of black holes. But what about our galaxy? We cannot see this energetic event from outside because you cannot measure the galactic center emission, light emission, because there's a lot of dust in the path of light. Okay, it absorbs. And we are in the, if we were above, maybe we could see. We are in the plane. In that plane, that light from the center is getting absorbed. Then what do you do? How do you know? So people came up, and that is Andrea Ghez and her team. You know, she got the Nobel Prize in 2019. They came up with this idea of looking at stars in the infrared, where the effect of the obscuration of light by dust is lower. They looked at stars very, very close to the galactic center. And this is what they found, that they are moving. All of them are moving around some object. It's like every star is binary with something. They are moving about something. And that something is your black hole. Using all these stars, this is actual data, the stars and these paths. So this is how these stars which are located in the center, towards the center, are known as S stars. They are special stars. They are heavy mass stars. They are formed in a very different environment than they are formed in elsewhere, of course, because they are very close to the black hole. But this is the trajectory. Using these trajectories, you can determine the parameters of the mass of this object. And this is the center of our galaxy, which is a supermassive black hole whose mass is of the order of 3.6 million times the mass of the sun. And you come to this mass by looking at the parameters of all these ellipses. Okay, that's how we know about this. And what was the next step after this? Because people were able, the EHT collaboration was able to image the supermassive black hole in M87, which is supermassive black hole in giant elliptical galaxy somewhere else, very far off, but it has to be much brighter than far off object we can see. And next target was our supermassive black hole in the center of our galaxy. By the way, black holes need not always be supermassive black holes. You know what are black holes, right? These very, very compact objects, such highly compact and dense that even light cannot escape. We can define a certain radius or a size depending on how much mass is present, but we don't know the structure within it because nothing can come out. So that's why it's all dark for us. That's known as the EHT people call that the region, that shadow. So so this is the image of the supermassive black hole which is present in the center of our galaxy. Okay, now I'll tell you a few things about this image. First is, you know that this image is not an optical image, or not in optical light, the light that we see. This image is taken at kind of radio waves, because only at these radio waves can you make a telescope. Many telescopes you can combine from, it's like essentially making a telescope the size of the earth. You are keeping lots of telescopes in different parts of the earth and using some special interferometric techniques to be able to image this. This is a technique which is mastered by radio astronomers over decades and decades, so they are very familiar with this technique. People are trying to do this with optical, but it's very, very tough. Radio wavelength, they are able to do it because of the large wavelength and the way we detect light using heterodyne receivers and so on, if some of you are engineers. But in radio, so this is a radio image, and the size that they have come up with is that, you can see this, within Mercury's orbit. And that is not, this is the shadow. What is this light? What is this light? Because black holes should not have any light. Then what is this ring that you are seeing? You have seen these kind of images, right? First and foremost, the shadow at the center, this region is where the black hole is. That is called the shadow region where the black hole is present. This light that you are seeing, this light is from a disk matter which is inspiraling at very, very high velocities, close to the velocity of light, into the supermassive black hole. Okay, so that as goes, because it's moving very fast, it heats up to such high temperatures that it gives off radiation. Very high temperatures, it's plasma obviously, millions of degrees, millions, much larger than that, several tens, hundreds, and that is giving off this radiation. Now, if this matter is going in, so where are we located? So all this is clear, that light is coming from there. Why is it not uniform? We would like it to be uniform, but our resolution, the way we see it, we are not, the various things that go in. One is resolution effect and other effects, which have details of the how fast the disk is moving and so on. I won't go into why it, ideally it should be more or less uniform if it is a proper perfect ring and simplistic assumptions. But once you put in complications associated with this, you see this. Because it's simulations, they were able to reproduce this. Next important thing I want you to consider is this is your supermassive black hole, right? And I am the sun. Then how will my disk be? How will my disk, I told you, it will be like this. I should not see the disk fully. I'm able to see the disk fully. Are you getting my point? Why am I able to see? And that is where the beauty of Einstein's general relativity comes into picture. What does Einstein's theory of general relativity tell us? It tells us that when you have a very, very compact object, massive compact object, then space is like warps. And that is why the light which was behind, which you shouldn't have seen, it bends and comes to us, isn't it? So that's why we are able to see the full ring, although we shouldn't be seeing. So we are able to understand this phenomena, we are able to reproduce it from simulations and therefore understand and image the black hole. So this is the beauty of astronomy, that multiple wave bands, multiple astronomers, all working towards one goal, at least in this area, trying to understand about the structure of our galaxy, the center what is there, and what are the various components of our galaxy. And what did I show you this donut and moon for? The telescope is so powerful that it can locate an object of size, the donut, if you keep it at moon. Okay. Well, NASA likes to use such analogies, so I brought it here for you. Okay. In fact, when they, I don't know if you have seen the press release for this one. They actually brought a donut and said, you see this? If I keep this at moon with this telescope, I can see that donut. Okay. So, I mean, it's just an analogy, just to give you an idea of what small structures you can see. Okay. So, understanding our home in galaxy is a work in progress. Okay. With this, I come to the end of my talk. I'll just summarize. So, as you know, the mapping our own galaxy is tough. We use multiple techniques. I talked about 2 of them, and different kinds of cosmic objects are employed. We, apart from proper motion, parallax, in the sky, we use the dynamics. That means the motion of stars are also used, not just position. And we know that our Milky Way, the structure comprises of spiral arms. It's not as simple. There is a bulge, there's a thin disk, there's a thick disk, and there is a halo. And the halo is made up of dark matter. And what is at the center is a supermassive black hole, which we have now imaged. So before I end, I just want to make a disclaimer that I've used a lot of images, but from the web. And finally, thank you for your attention.
Thank you, Sarita, for this wonderful, very illuminating talk.
Thank you.
So now the floor is open to questions. Anupam Ghosh will assist in this.
Yeah, you can raise your hand and we'll bring the mic to you.
Hello. Thank you for the talk, Dr. Sarita. So I have one question regarding the coordinate systems, right? So we have coordinate system on the Earth, right? Latitude, longitude. And then we have Earth-centric coordinate system when we are observing from the Earth, right? So what kind of coordinate system is used for the telescope outside the Earth? Outside the Earth. Say you have a James Webb telescope, right? So whether there is any universal coordinate system which which is in preparation or is something, or it has to be always Earth-centric?
It is Earth-centric because and Earth-centric is not one coordinate system. There are in fact multiple coordinate systems. Because when you say the way we define, and it's analogous to what you define as latitude, longitude on Earth, we are able to define latitude, longitude on Earth because of the axis, the polar axis and the equator. You use these two to define. Similarly, when you go to the dome of the sky, you need to define an equator and a pole, and that can be very different. So it can be related to the Earth, but it can be related to the galaxy also. The plane of the galaxy can define your equatorial plane, right? So that is galactic coordinate system. Then you can have the plane where the Earth is moving around the sun. That can be used as an equatorial plane, not just the Earth's equatorial plane. So there are multiple coordinate systems which are used, which is equatorial, horizontal. I'm just giving you different names. So ultimately, the one which is where you use the equator of the Earth, that's the equatorial coordinates, that is most commonly used by astronomers. And even if we go outside, ultimately we use that because that is kind of universal which everybody uses. But if you are trying to map the galaxy, for example, then we prefer to use the galactic coordinate system. So surveys which map the galaxy use the galactic coordinate system. And then if you want to convert between the two, there are equations to convert from one, because it's spherical trigonometry, you can convert from one to the other. If you're dealing with solar system objects, it makes more sense to work with the ecliptic coordinate system. Okay.
Hi, ma'am.
Hello.
Thank you for the talk. So I have two questions. So one is, when did we first came to know about that our galaxy is spiral? And
okay, first we know it's long back. We know that it is flattened long back. Because if you look at the night sky also, you see that you will see the band is in specific direction. So when they started making even that Herschel's map, you can see that star count, that is very flattened. It was as early as that we started coming to know that things are flattened. But the fact of a spiral galaxy, that it is started when the debate when it started. And when it was first shown that there are spiral objects which are flattened, which are located outside our galaxy, that is when they started thinking along those directions and started thinking that yes, ours is a flattened object. So it is very likely to be a spiral galaxy. But mapping the spiral structures is very difficult, and that has been going on for quite a long time.
And with Gaia, is that it's going outward from us, or it's...
No, that was not Gaia going out. That is just a simulation. Okay, what Gaia does, Gaia is located there are certain points, okay, they are called Lagrangian points, and this Gaia is located at one place which is located very close to a certain point. It's in the shadow of the Earth. Okay, so as the Earth is moving, it will always remain in the shadow of the Earth. That's called, it is not moving away from that point. It is at a constant distance from Earth. But from there, people have mapped the stars. And once they have mapped the stars, they have made a simulation. In that simulation, they are showing that as I move away, how the Milky Way looks like. So that is not Gaia moving away. That is using Gaia information, database of stars. They have made a 3D structure of galaxy and showed that if I'm moving away from there, how the galaxy and the star distribution will look like. Okay. Is that clear?
Yeah.
Okay.
Thank you.
Hi, Dr. Sarita. Thank you so much for the talk. It was very enlightening. So you said that the galaxy is warped. So does that have something to do with space-time being curved? Because like a galaxy is after all just composed of particles that have mass. So like, is that somehow warping?
No, that warping, usually space-time curvature and warping are used in very loose terms. Okay, in actual general relativity, we use other technical terms. So this warping just tells you about the bend, why it is bent. And the theories about this, it is seen in the outer regions of galaxy where the mass is very less, of course. But the mass distribution of the other, even of the dark matter, is not that it is exceeding much more, because the rotation curve is more or less constant. So if I take uniform shells of mass, then it is more or less constant. So, but then why should warp happen only at the edges? It should happen everywhere if it is dark matter, but it's not. So what people postulate is it's possible that there are other galaxies close by. It could be related to dark matter distribution, because we are assuming some distribution. If there is some other distribution, then maybe dark matter is one contention. But very often, because of some interactions with close by galaxies and so on, people have seen that if there are galaxies close by and trying to interact, then the warping begins. But the answer is not very well known. We don't know, because these are on such large scale, happening on such large scale, and we don't know, at least in Milky Way, what is responsible. And important thing to understand is when we are doing this observation, we are just sampling a very teeny weeny slice of time. You know, the observations, what we know as observations, started 400 years ago, right? Let us say 400 you want to call, or 500 years ago, when Galileo made the first telescope, but actually 400 years, let us call it. That is nothing in the lifetime of a star. Forget the lifetime of universe or lifetime of galaxy. So with these limitations, just imagine, we are trying to build so much. We are trying to understand the life of a star. The entire life of a star we know today, only from this snapshot. So those are limitations we have to work with, and with those limitations, people have come to the fact that probably, that's why we don't know clear-cut answers. Basically, I'm trying to tell you that.
Hello, ma'am.
Hello.
Thank you for your talk. Like we see in newspapers like this, so-and-so planet has been discovered. So those planets were attached to, some other stars. So they are very far away. So how do we detect them? Like, how is it possible to?
Okay, that requires a completely new set of lectures and a completely new talk, which I'm very happy to give. But in the interest of time, I will just tell you some things, some methods. There are at least 3 to 4 methods. These are called extrasolar planets. They don't give off light, right? So your problem is this: they don't give off light, yet we are able to detect them. And particularly now we are able to detect them because you have space missions, so the effect of atmosphere is reduced. First is foremost is direct imaging. But if you do direct imaging, the light from the star will overwhelm, and those guys will not emit in optical. Earth, for example, emits in infrared because of its temperature. So those planets will also emit in infrared. And so people have done direct imaging in infrared, particularly if you have seen James Webb Space Telescope and so on, that works in near to mid infrared, where the emission from the star becomes much less and emission from planet becomes much more. Okay, so mid infrared direct imaging is one, but that requires very high resolution. You should be able to see very, very clearly, like donut on moon kind of. Not that, if you have that, very good, but normal telescopes are not able to work at that scale. So there are other indirect methods. For example, you use the fact that it's a binary system. Okay, binary system in the sense that if one object if the star has a certain mass and the planet has certain less mass, both of them are moving around a common center of mass. This is moving much less, this is moving much more. If we are able to sample the motion of the star very carefully, the radial motion, that motion about the center of mass, which people are measuring, then they are able to locate how much this motion is, and therefore what should be the mass of this for it to be moving here. Okay, so this is one radial velocity method. There are multiple methods. Okay, then transit method is another method where they start observing how much light is coming from the star very carefully, very less scope of error, and then they observe that eclipse if the plane is like this, in the plane of, again I need my so if this is your plane of the sky, and if the planet that orbital plane is like this, then the star is here, right? Not plane of the sky. If I'm not talking of plane of the sky, I'm talking if this is the plane of the sky, and in my line of sight, the planet, the plane, orbital plane is in the plane of the line of sight. It's not in the plane of, it's perpendicular to the sky plane. Are you getting? If it's perpendicular to the sky plane, that means sometimes the star, the planet will come in front of the star. That's eclipse, correct? Sometimes it will go behind. When it is going behind and when it is coming in front, the starlight changes. The combined light, what you will be measuring is the combined light. So basically you are seeing the eclipse happening. So you will see a small dip when the planet is passing in front of the star. People use these very, very sensitive techniques to be able to tell. This is the transit method, that was a radial velocity, there are more methods. Gravitational lensing, blah, blah, blah. Yeah. Yeah, the point is you shouldn't look very far because these are small teeny weeny effects. The thing is I will do close by objects first. Second, we know that if it's a very massive, huge star, then the probability, it will have a lot of radiation. Then what's the probability if it's a main sequence star like our sun? Main sequence means in the medium phase of life. Okay. Then if it's in the medium phase of its life, then what is the probability that a planet will be present? If it's a very massive star, then there will be a lot of radiation which may be present. So people usually start by, it's not that planets cannot be there, but people usually start by considering sun-like stars, okay, which are similar to the sun. They are the K and M and F and G type of stars. They concentrate on those because the light is also less and it won't overwhelm the planet, for example. So they use some of these techniques to be able to do.
Thank you, ma'am, for the presentation. I just wanted to ask you about one of the planets, like you said, the Pluto was demoted in a certain sense. But there are a lot of people trying to put up that there are always 9 planets and that's how these are. And what's your view or take on that?
Okay, so it depends on how much attachment you have to Pluto. Okay, because there was a very solid reason which was given for demoting. Now you can always say that I don't like it. It depends on where you stand. Okay, so if you're asking my personal view or if you're asking in general view, what astronomer? See, if you're asking my personal view, the definition of planet seems robust now, and you should understand why Pluto was demoted. Why suddenly people got up one day and said, nahi, hame Pluto acha nahi lagta, right? There's a reason for that, because there were some objects which were even larger than Pluto, which they found in the asteroid belt. And farther away, with improvement in telescope size, we are able to see farther. So there were objects which were found in the Kuiper belt, say, which were larger in size than, or similar in size than Pluto. So now the question came, either you call Pluto a planet, then you have to call all of these as planets, and as more and more objects start coming, you have to start calling. So your planet's definition will always keep changing. And as students, you will have to by heart 20 planets. Probably they didn't like that idea, so they decided. So you see, it's not very confirmed. So they said, no, instead of that, let us give a more robust definition. And they included one more definition. So the definition of the planet now says that it has to be moving around the sun. It should not be satellite of any other object. Okay. But none of these objects, so I mean, you can have moons which are larger than Pluto. But so that is removed. But all these objects are moving around the sun, and it has to be spherical in shape. It should not be small enough that an asteroid also is called planet. So these were spherical objects, but it should have enough mass to have cleared its neighborhood. And that the other objects did not satisfy. Although Pluto to some extent satisfies when it goes out, but that's not a robust definition, because that definition now comes in terms of mass and so on. So that's the reason why Pluto was demoted. So once you understand this, you say, yeah, that's fine, unless you like Pluto a lot.
Hello. Yeah, so my question is, recently in the news we saw that, a solar flare had escaped from sun and it might cause power cuts in different parts of Earth. My question is, one is, how exactly does a solar flare travel through a medium? And secondly, is there any way that, we on Earth can use solar flares to our advantages, like, convert it to something
that
useful?
Is very far away from what I work, but I will try to answer some part of your question. Whether we can use it to our advantage, I'm not an expert to be able to answer that, but I can answer some of the other things that you asked about the solar flare, which is like, what makes you think they should not be able to travel? It's light and particles. Ultimately, light can travel, right? And so can particles. So it travels through that medium and reaches us. And it affects these grids. We think it will affect grids because these are highly, highly charged particles. So that will affect. In fact, people are studying, even ISRO and all these space missions, when you are sending them out, you have to see the space weather into account, because these particles, particularly when there's a solar flare, can affect the body of the spacecraft or whatever that they are traveling in. So what was your other question? So I've answered this question that there's nothing stopping them from traveling. It's radiation and charged particles. And secondly, they will affect, but whether they can be utilized in some way, I don't know. If they were as regular as wind, maybe we could, but here we don't even know when they're going to come and what will be the intensity, from which part of sun it's going to come. So that is pretty random right now. And to harness it, you need more information, a lot more information that what we have now. This is what I can think from my perspective, but probably a solar physicist can answer that better.
Rukmini, you have to-
I have one question.
Yes.
So you mentioned the elliptic type of galaxy, spiral and
Yes.
irregular.
Yes.
So is it to do with the formation period that they take these shapes, or?
Yes, it's a very, very nice question. Why do galaxies have these broadly these shapes? So it is believed that particularly we find that in the beginning, these elliptical galaxies, because they have this 3D kind of structures, they are believed to have been found mostly from mergers of many, many things coming together. And that is why they don't have some specific rotation. Whereas these spiral galaxies seem to have been formed in some kind of isolation, some mergers, but relatively less number of mergers, which did not affect its organic evolution as a whole. But this elliptical, and this is also known now from the fact that some elliptical galaxies have not one center, but they have 2-3 supermassive black holes. That means these galaxies would have merged and they have slowly gravitated towards the center. So this is the current understanding, that elliptical galaxies are formed now, what we see, and some of them are huge, like M87, much larger than what the spiral galaxies are. And that kind of thing, and they are older stars. There are many reasons for us to think that they are formed from mergers. So it has to do with the formation mechanism as they evolved after being formed.
Thank you.
Okay.
Thank you for the talk again. Something about the S stars when we were analyzing the whole supermassive black holes. Some of the stars had an orbit that came very, very close to the supermassive black hole, but they seem to also go away after that. But from my understanding of supermassive black holes is that once you enter the hole...
You're not the hole. They are still far off from the hole, very far. So that radius is called the Schwarzschild radius. As you see, it is smaller, as something like sun's diameter from the picture. You remember the picture I showed you, the actual picture?
If you could...
The picture of the actual image of the supermassive galaxy, the next slide.
Yes, ma'am.
So the size of the image was Mercury's orbit, approximately the size. And the size of the shadow was roughly, you can say, size of sun or slightly larger. So you see those stars are still pretty far away. But that doesn't mean stars will not get affected. There are a number of S stars who get such a kick that they are thrown out. They are thrown out so far that they acquire such great velocities that they travel to the edges of the galaxy because they come very close. Okay, because it's not that everything that comes in has to be, there are other motions, the elliptical motion, you have to consider all these motions together. So in this motion, some of them get a kick and they may be thrown out. Then there may be some stars which are torn apart because they start coming very close to the galaxy. So that's not close at all. It doesn't come close. It cannot enter. I mean, as a whole, it cannot enter and come out. Okay.
Good evening, ma'am. So as you mentioned, there's a supermassive black hole at the center of a galaxy. So my question is, what are the effects of Hawking radiation on the black hole? Whether it's in a state of equilibrium by gaining energy
See,
from...
let's not go into Hawking radiation, because first you should know what Hawking radiation is. So effects of Hawking radiation. Do you know what Hawking radiation is?
So it's a black body radiation that occurs...
No. That's the thing. So Hawking radiation, I don't want to get into this. It is some very special kind of particles which are produced from, I don't know. If you want, I can tell you the definition. But I'm not sure it will help answer or enlighten, but I'll still tell you. So there are particles which can be created and destroyed in vacuum when there's nothing. Okay, which are continuously created, destroyed, even in vacuum when there's nothing. So if such a particle pair is created, particle pair means particle, antiparticle. So particle, antiparticle, if it is created close to the black hole Schwarzschild radius, suppose one of them goes inside and the other goes outside, then they become real particles because one is lost. That is Hawking radiation. It has nothing to do with black body. So you cannot say effect of this. Secondly, this is something that was postulated and people work a lot on it, but that is mostly in theoretical domain. Okay.
Thank you.
Hello, thank you, ma'am.
Yeah.
And I wanted to ask you, like, We have put some time into predicting what the future of the universe will be. Like there are various theories. I wanted to ask, like, how did we come up with them and how can we predict them?
Future of the universe or future of the sun?
Like the theories about the future of universe.
Yes, but that has to do with how we define our past. And we don't know our past very well. Because there are infinite models of the past, there are as many number of models of the future, if you understand what I mean.
Yeah,
right?
yeah.
Because all we know, if you're talking about cosmology, is cosmic microwave background radiation. But to reach that cosmic microwave background radiation, people postulate the presence of inflation and so on, which is something people still don't completely understand. That's why you have a really, really large number of people working on this. And the number of parameters are so huge that you tweak some, you get something. But they all end up here. But then that also defines how we will evolve. That has to do with the density of matter and mapping all the matter which is present in our galaxy. Not our galaxy, in the universe. And that we have not been, if you want from observational perspective, this is all theoretical. But ultimately, it has to be driven by observations. To do that, you need to know how much matter is there. Right now, we do not, what we know is the luminous matter that we see, that is few percent, and then 4%, and then 25% is dark matter, and then there's something dark energy, which we talk about. Yeah, so these are all theoretical concepts. So the future is, unless we know the observations and are able to get a very good grasp on it, we will not be able to tell with certainty how we are going to evolve.
Okay, ma'am. And how did we, like, what was the reason why we came up with this theory of dark matter and dark energy?
Dark matter, I've already told you.
Yeah, yeah. But
what
like,
was that? The rotation curves of galaxies is what has given rise to dark matter.
Okay, okay.
Okay, that's the only reason. Because we are not able to explain it. But I want to also tell you that there's an alternative theory which people are coming up with, saying that's called MOND, or modified Newtonian gravity, which says, so we should, this is one theory which is most accepted, because the dark matter, because it's simpler and able to explain many things. But people are coming up with this modified Newtonian gravity theory, where they think that the Newtonian gravity as we understand it may be very different on galactic scales, because there's no way for us to tell. So if you modify the Newtonian gravity itself, then maybe we are able to explain the rotation curves of galaxies. So there are people who are working on that aspect as well.
So dark matter.
That's the experimental evidence. No, actual, what composes of dark matter. Not yet. People are trying very hard. They're working. There's a lot of surveys being carried out to try to understand more about dark matter. Okay. No, there are people who are questioning. That's why I've told you about it. There are people who are questioning. But the thing is, the dark matter theory is more popular because it has been able to explain a number of observations apart from this. I didn't talk about all of them. But now people are slowly working on modified Newtonian MOND theories, even to explain those other things. But then the number of parameters become very large, so they're saying this is simpler and we are able to do it. But it doesn't mean that it is wrong. I mean, but we need to evolve and see how it goes.
So thank you. I love the talk. I wanted to know what happens when two galaxies collide, because Andromeda is going to in 4.5 million years.
Did you know one galaxy is already colliding with Milky Way?
Currently?
Yes.
Oh.
Okay.
I heard that Earth is not going to be affected at all,
No,
but I just
no.
want to know what exactly happens.
Okay. So when first and foremost regarding that collisions, it is believed, what people have found, which I didn't talk, lack of time, is that in the Milky Way towards Sagittarius, there is a group of stars which is believed to be from another spheroidal galaxy, which its constituents, the way it is composed of, is slightly different from the stars in the vicinity. So people have postulated that this is another spheroidal galaxy which is kindly passing through. Okay, that's called Sagittarius dwarf spheroidal galaxy. And those stars people are studying, that they have even identified stars which belong to that galaxy versus the stars which belong to us. Okay, and when galaxies collide, it is not one hard body colliding with hard body, right? There's a lot of dynamics of gas, dust, and stars which are involved. And stars occupy a teeny weeny space in the whole galactic volume. That's why we are not going to get affected. But when this matter passes through, people do simulations. What they do is to understand, because in real time you cannot observe them coming close. All you will see is coming, we know that they are coming close, but you can't see the entire process because that takes very long time scales. So what people do is they do simulations. From the simulations, they try to understand how the galaxies interact. So there are simulations where the stars get affected, the galaxies can pass through, some stars get affected, because ultimately it is gravity. So if there is a group of stars which is coming towards me, how I will respond, correct? So that they try to simulate from these large number of simulations, how the gas and dust will respond to this matter which is coming. It's all gravity and motion. I am also moving plus gravity effect. Once you know these dynamics, you should be able to put it all together and see how it is going to respond. Because actual collision, it's not, the probability is very low because the volume occupied by the stars is very small. Okay? So they actually pass through. If it's a head-on collision, they pass through and then come and they sometimes merge, and depends on the size, depends on how they are colliding, the angle. People have done a lot of simulations regarding.
Hello, ma'am. Thank you for the wonderful talk. So, ma'am, my question is the spiral galaxies, why does gravity allow those discrete spiral arms? I mean, like.
Okay. Yeah. So, the clear answer for that again is we are not very sure. But there are again theories which tell us why this could happen. And one of the theories has something called spiral density. There are density structures which are from the matter gets, which is gas and dust, need not be stars. Gas and dust tends to form spiral structures because of some motion perpendicular to the disk of the galaxy. The galactic motion is, if everything was in a plane, one star thickness, everything would move. But in reality, it has some thickness. So there is some perturbation or some motion in this direction also. Some component of its motion can be in the direction which is perpendicular to the plane of the galaxy. And that motion can give rise to some kinds of density structures, density waves it's called, so that when gas and dust passes through this slight density perturbation can enhance the density, so that when gas and dust pass through these kind of high density wave region, then it can get condensed and form new stars. So the new stars are always found to be formed in the spiral structures, in spiral galaxies, because as they move into these density waves, this is one theory. Then there are other theories, of course, but I've just told you the oldest one.
Ma'am.
Yes.
Thank you for the talk. I have a doubt regarding black holes. So you mentioned the accretion disks, right? How do they stay in like an orbit around the black hole without having to cross the event horizon? And since it also like radiates.
Wait, one question at a time.
How does?
Firstly, these are rotating black holes.
Yes. So
that is why they have accretion disk around.
Yeah. And how does it stay?
It's not staying. It's moving in. Matter moving in.
But how does it like not? How does it stay around it, but like not
it is spiraling in.
Yes, but how does it not spiral into the black hole?
It does spiral into the black hole. Yeah.
So since it like emits radiation too, right? So it like eventually has to pass. I mean, eventually has to fall into the black hole. So if a part of it falls, then everything around it also you like continuously fall.
Yes, it, right? Yes. Matter is continuously flowing in, and the stars stars which are close by, that will also break up and become this material which is flowing in. So over time, the black hole becomes bigger, bigger, bigger in, bigger in the sense only more massive. And as it becomes more massive, the Schwarzschild radius, that radius which we call, that also is going to increase. It is increasing. Matter is continuously falling in. If not, it will not remain the same. Okay.
Okay, thank you. So, would you like to take more questions here? Or?
I am fine either way.
Okay, a few last questions if anyone has. Go.
Ma'am, thank you so much for the talk. I actually had a couple of questions regarding black holes. We know that mass goes into them, but where does that mass go exactly? Because matter can need be destroyed.
I don't know. I don't think anybody knows. Okay. We don't know what's inside. Okay. Whether it is a point, whether it's toroid, nobody knows. Because there's no way to know.
Okay.
All we know is what's outside.
Okay. Also, I also heard a lot about these things called quasars, so I was actually confused what those are.
Okay, so quasars are some kind of supermassive black hole, very, very far off in distance. These are very, but they are so energetic events that they look like stars, but they're actually very, very far off galaxies. We know by looking at the Doppler shift, and they know that they're receding and so on, so we know its distance. They're really very far off supermassive black holes, or they are also called active galactic nuclei, which is present in the center of some galaxies. Okay. So quasars are that. They're quasi-stellar objects. They look like stars. You can't see the galaxy because they are very far, but they are so energetic that they look like a star even at this far distance, which means they have to be really energetic.
Okay. All right.
Okay.
Thank you.
So one more question. Yeah.
Yeah, sure.
So maybe very basic question. So when solar system was formed, right, and when Earth was formed, the matter accumulated in 3D structure, which is Earth, right? But the solar system is quasi-planar, right? And galaxies, spiral galaxy is also quasi-planar, right? Or planar, let's call it planar, right? For all the practical purposes. But when the galaxies come together, it is a cluster which is 3D cluster. Universe is 3D. How does all this
Okay, so
so when the matter accumulates, right, is it the density that matters? Is it really, what really matters to make it a 3D structure versus 2D? I mean, how?
If you look at gravity as a force, you know Newtonian gravitational law, it goes as R, radial. There is nothing to make it a plane, right? It should be a sphere. Everything should be a sphere. Yeah, but Earth is not a full sphere. It is a bulge. Why? Because of rotation. So the moment you introduce, spin, rotation. So because of this, some symmetry breaking happens. And that is why you find planar structures. If you have a group of objects which are moving with certain rotation, then, and which, like for example, in the case of the solar system, these planets formed from the same molecular cloud which began rotating. The whole cloud was rotating in the same way. That's why they formed in the pattern. Similarly with spiral galaxies, but not elliptical galaxies, because they came from different directions after they were formed. Okay. So ultimately it is a 3D structure. The flatness comes, toroidal structure, like whether you talk about accretion disks around black holes, you talk about disks around stars, you talk about any kind of disk structure, that appears because of rotation. The moment you have rotation, it will flatten it in a direction perpendicular to the rotation axis. So the sun is rotating. Even now, the sun is rotating. So you have, and the rotation axis is roughly perpendicular. Why do I say roughly? Because things have changed, some interaction here or there. So that's the reason. I hope that answers your question.
Thank you. Thank you everyone for coming, and thank you, Professor Sarita, for this fantastic talk.